So the recording has started. So we will wait for a couple of minutes and then we will start. Can any confirm, is my screen is visible and am I audible?
Yes, sir.
Thank you. Okay, so it's 6 o'clock. Let's start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. So this is a 12-week course actually, and we are in the fifth week of live session. Okay, so if you have any doubts up to this week, you can ask me either now or later. Okay, so let's start. So in week one, we have discussed about different algebra of sets, set theory, classes, collection, ring, sigma field, etc. Then in week two, we will discuss about the conditional probability, the multiplication rule of probability, total law of probability, and then Bayes theorem, the cumulative distribution function and its properties. In week three, we have discussed about moments, the relationship between central and non-central moments, the characteristics functions, and the skewness and kurtosis, the interpretation of those skewness and kurtosis, different kinds of skewness and kurtosis as well. And then we have discussed about Chebyshev's inequalities. And at last, we have discussed about the discrete kind of distributions like Bernoulli, binomial, geometric, negative binomial, hypergeometric, etc. In week four, we have discussed about like Poisson distribution and then different kinds of continuous distribution like like exponential distribution, beta distribution, gamma distribution, etc. So today we have discussed one very famous or very common continuous distribution, which is like normal distribution. Today we will discuss about like mainly normal distributions, different properties of normal distributions, and the like the how to standardize the normal distribution as well, and then the log normal distribution. Also, there is one concept that is quite used in our statistics, that is central limit theorem. We will then solve some numericals based on these normal and log normal distributions as well. Okay, so let's start. This is the standard normal distribution table. Okay, we will come to this slide later when we will solve numericals. Okay, so let's start. Okay, so the first one is like, what is central limit theorem? In short, we will call it CLT. Okay, so suppose like we have a sequence of random variable. Okay, let me write here. If we have a sequence of IID random variable, that is independent and identically distributed. That is IID, independently and identically distributed random variables. Then the distribution of the sample mean, then the distribution of the sample mean, that is X bar, or the sample sum, that is summation Xi, under certain regularity or condition. Under certain condition is approximately normally distributed. Okay, as n is large. Okay, so this is what the central limit theorem says. Suppose we have a different sequence of random variables, like suppose x1 follows d1 distribution, x2 follows d2 distribution, xn follows dn distribution with some parameter values, obviously. Okay, then suppose their sum, that is summation of xi, is eventually or ultimately follows normal distribution with some appropriate parameter value. Okay, so this is what the central limit theorem says. Then let's start about the normal distribution. This is also called Gaussian distribution actually. Okay, Gauss has used this distribution for error analysis purpose. Okay, so it is also known as Gaussian distribution. So suppose x is a random variable which follow normal distribution with its parameter mu and sigma square. Okay, then x is said to be normally distributed random variable. Okay, and the PDF is like one upon root 2 pi sigma e to the power minus of 1 by 2 x minus mu upon sigma whole square. X belongs to the real number, mu belongs to the real number, and sigma is positive. Okay, so now we have two parameters here as well. Okay, as you may recall that in previous classes, we we define the moments like mean, variance, and other terms with the help of those parameters. Here, coincidentally, we have one good news, like the average value, which is the mean value for the normal variate, is actually the first parameter itself, mu. And for the variance, it is sigma square. Okay, so the two parameter itself, the mean and variance for the distribution. Okay, so it is beneficial for us. Okay, also like here, always remember there is one note actually kind of thing you may say. X is said to be normally distributed with mean and variance. Okay, always write like this. Okay, this is the standard notation actually. Okay, suppose some people have written like this, like if y follows normal with mean and its standard deviation. So it is like wrong notation. Okay, always remember if we have like given n within bracket the two values, then that is mean and variance only, not mean and standard deviation. Okay, so we have some properties of normal distribution as well. So like expectation and variance is already written here. Okay, there is one more note actually. All the odd order central moment is zero for the normal distribution. Like for the normal distribution, all odd order central moments is zero. Okay, all odd order central moment is zero, and even order has also some particular form actually. So like expected value of x minus mu k equals zero for all k is odd. Okay, the central moment x minus mu power k, and obviously the non-central moment is like expected value x minus mu cos power 2m equals sigma to the power 2m, then 2m minus 1, 2m minus 3, 3 into 2, not 2, it comes out to be 1 here only, into 1. This is the uh, even order central moment for m equal to 0, 1, 2, and so on. Not 0, it's come from 1 only, 1, 2, 3, and so on. Okay, so this is the property for the normal distribution, that the all odd order central moment is 0 and even order has a specific form which is given here. Okay, so yes, we can calculate the skewness and kurtosis as well. So like the third order central moment comes out to be 0, and the fourth order central moment is comes out to be sigma to the power 2. We should take the value m equal to 2, so it's 2 cross 2, then 2 into 2 minus 1, then 2 into 2 minus 3. That's it. It comes out to be sigma to the power 4 into 3 into 1, which is comes out to be 3 sigma to the power 4. This is the fourth central order moment. Now, skewness, that is beta 1 coefficients, which is mu3 square upon mu2 cube, comes out to be 0 because mu3 is 0. So comes out to be 0. This implies it is symmetric in nature. The normal distribution is symmetric in nature. Then again, let's calculate beta 2, which is the fourth central order moment divided by the square of the variance. That is the square of the variance. Okay. So it comes out to be 3 sigma to the power 4. It's divided by the variance is sigma square and its whole square comes out to be 3. Okay. So the beta coefficient comes out to be 3, which implies the gamma 2, which is beta 2 minus 3 comes out to be 3 minus 3 equals 0. Okay, so this means what? This means it is neither, like this is the reference point actually, that is mesocotic in nature. That is neither too peaked nor too flat. Neither too peaked nor too flat. Okay, so this is the normal distribution. Now the next thing is the moment generating function, MXT. As you know, the MXT is defined as expectation of e to the power tx, and when you solve, you will find out the MXT for the normal distribution is e to the power mu t plus sigma square t square by 2, half of sigma square t square. This is the moment generating function for the normal distribution. Okay, there are some properties of the normal distribution. The first one is like, suppose X follows normal distribution with parameter mu and sigma square, then we transform this with the help of normal distribution like a random variable y, which is ax plus b. Okay, this follows again the normal distribution with parameter a mu plus b and a square sigma square. Okay, so this is the, like the transformed random variable. Usually the transformed random variable from the normal distribution is most of the time normally distributed. Okay, also this property is specially known as linearity property actually. Okay, now we have one more property that is also called standardization of normal distribution. Okay, so it is usually denoted by z. So what is this? This is like, suppose x is a random variable which follow normal distribution with mean mu and variance sigma square. Let me write here. Let x is a normal random variable with mean mu and variance sigma square. Then a random variable z, which is transformed random variable in such a way that x minus mu upon sigma. This follows normal distribution with mean 0 and variance 1. Okay. Or you can say x minus expectation of x upon standard deviation of x. This approximately normally distributed, but here since x is normal distribution, it is normally distributed with mean 0 and variance 1. This process is called standardization of random variable. Okay, so this may apply on different kind of random variable as well. Okay, the standardization process. Okay, so this z random variable is known as standard normal variate. And when we will solve some numericals based on this topic, you will find out that we will use always the standardized variate as instead of like normal variate, because as you people may know that the PDF is not integrable actually. So that means the cumulative distribution function of this normal distribution is not in closed form. So we use some approximation method, and with the help of those methods, we have a normal table actually. And that normal table is not for all values of mu and sigma. that is for the standardized value of mu and sigma, which is here. Is like standard normal distribution. Okay. And yes, every table has a picture, has a graph actually. Here you can see this is the graph. Here the following values are given for this 0 to z only. Okay. Also, we have one or two more properties of normal distribution. Actually, there is a lot of property, but we will discuss some of them as well. Like, yes, since z is a standard normal variate, z follows normal 0, 1. So what is the PDF of z? Okay, I've written it wrong. It's 1 upon under root 2 pi sigma, and sigma comes out to be 1. So under root 1 upon 2 pi e to the power minus 1 by 2 x minus mu upon sigma. So mu equals 0 and sigma equals 1. So that means z only. So half of z, or let me write in a clear manner, it's z by 2. Okay. So this is the PDF for the standard normal variate. Here there is no mean and no variance, only the random variable z is there. Okay. And z is greater than 0. Not greater than 0, it belongs to R actually. And since there is no mu and sigma square, then we can split. So this is the PDF for the standard normal variate. Okay. Also, we have some properties. So like first thing that we will usually do, the integral value of this usually denoted by like capital phi z. Okay. So it's usual notation. You may either use or may not use, but it is usual notation. Since its integral is not closed form, so we may use capital phi z as its PDF. Okay. Or integral form. Also, one more property is there, like okay, since it is symmetric in nature, so we have like phi of its capital phi, obviously, z plus phi of minus z, it comes out to be 1. Okay, this is one of the property that we will use continuously when we solve the numericals based on normal distribution that we will show later. Okay, so this is what about the normal distribution. Also, if you may try to understand or visualize, you may find phi at 0 comes out to be for 0.5. Actually, let me draw a graph actually for you. Okay, so it's like suppose it's a symmetric curve. Okay, kind of. Obviously, it is a symmetric curve because it's the normal curve. Okay, so we have like okay. So the first one is, suppose this is our mean value. Okay, and this is the standard normal curve. Okay, so it is our mean value for z, which is equal to 0. It is at z equal to 1. It is at z equal to 2. It is at z equal to 3. Similarly, here as well, z equal to minus 1, z equal to minus 2, and that's z equal to minus 3. Okay, so there is some properties of normal distribution, and those are like the first is the probability that z lies between mu minus sigma to mu plus sigma. Okay, actually, I have written one thing wrong. That is not exactly wrong, but the notation is wrong. I should write here x instead of z. Okay, z and x both are kind of similar thing. Okay, z is x standardized version of x. Okay, so I have written here as a in picture z, but in here x form, or you can write here x as well. So in this, the properties like 6, 8, 2, 6. Okay, so that means what? That means in one sigma limit, for if x is a normal random variable, then in within a one sigma limit, the total probability distribution is 68.26%, 0.6826. Okay. Also, we can write this like this even if you want. It's z minus 1 to plus 1. This is the same value, 6826. Okay. Also, this can be visualized here as well. So it means 68.26% values lie within the 1 sigma limit. And what about the 2 sigma limit? It's 95.44. 95.44% of the data lie within 2 sigma limit. Okay. So if you find, if you calculate, obviously, you may find that the probability distribution within 1 to 2 sigma limit from the left as well as from the right is approximately 13.59%. That is 0.1359. And since it is symmetrical, it is 13.59%. Okay. And when I'm talking about the 3 sigma limit, it's the 3 sigma limit, it's 99.73% approximately. Okay. So this comes out to be the probability distribution within 2 sigma to 3 sigma limit from both the side is approximately 2.14%, 2.14%. So this is only for the normal random variable. Okay. Those random variate which is normally distributed. This is their probability distribution. Within 1 sigma limit, 68.26% of the data lie. Within 2 sigma limit, it's 95.44%. And out of those 95.44%, only like 27%, approximately 27.18% of data lie within 1 to 2 sigma limit. And around 34.13% of data lie within 0 to 1 sigma limit on both the sides. Okay, so this is the fixed value for any value of mean and variance or any value of parameter. Okay, so that's why it is very important distribution in our statistics and probability. Okay, so obviously we can write here like this. If you want, we can write probability that mu minus 2 sigma x mu plus 2 sigma, it comes out to be 0.9544. Or if you may want to write minus 2 to z to plus 2, it comes out to be 0.9544. Both the statement have the same meaning. The first one is normal variate and the second one is standard normal variate, nothing else. And the third one is the mu minus 3 sigma x mu plus 3 sigma. It comes out to be 0.9973, which you can write minus 3 z plus 3 comes out to be 0.9973. Okay, so this is the some fixed property of normal random variable or normal distribution. Okay, so up to this point, anyone have any doubt? Please, you may ask. Or we have one or two more topic actually. But before that, since normal distribution is very famous, as we have told already, there are some approximation to normal distribution. Okay, so the first one is like approximation to normal distribution. As we have already discussed in the previous class, if you people may remember, there are some distribution, actually every distribution are connected with any other distribution via some transformation. Okay, so here, since everything is like connected to normal by some transformation, so let's write or understand some of them. The first one is like binomial to normal. Okay, the first one is binomial to normal. So like what? Suppose x is a random variable which follows like not normal, it's binomial distribution with parameter n and p. Okay, so as you people know, since x is binomial random variable, the expected value of x is np and the variance of x is np1 minus p, which is also written as q. Okay. Now we have learned about the central limit theorem and we have learned about the standardization of normal random variable. Okay. Suppose if n is large, n turns to infinity means n is large, and usually when we take n equals 30 or more than 30, we have considered a large sample. Okay. So we may consider a large sample when we have 35 sample, we have 40 sample, we have 100 sample, but usually more than 30 gives a significant kind of result. Okay. So suppose n is large and p is obviously kind of 0.5 in the range, just like in the neighborhood of 0.5 in that case, then our random variable y, which is x minus np upon under root of np1 minus p. This actually approximately normally distributed with mean 0 and variance. Okay. So this is one approximation that x is a normal random variable, but its transformed version, that standardized version, converges into a normal distribution. Okay. And in the similar manner, we have a Poisson as well, like Poisson to normal. And how? Like x follows Poisson distribution with parameter lambda. And if lambda is large, then in that case, x minus, okay, let me write one more thing. You people may remember the expected value of x for the Poisson variate case is lambda, and variance of x, can anybody guess? It's lambda again. If you people may recall, you may find that first three moments of the Poisson distribution is same actually. Like mu3 is also lambda for the Poisson variate. Okay, but we don't need mu3 actually here, but it is right. Okay, so like again y, which is x minus the mean value lambda, the standard deviation, which is under root of lambda, follows normal with mean 0 and variance 1. Okay, so this is the approximately or say asymptotically normally distributed random variables. Okay, the y1. Okay, so also you people may remember in the last class we have discussed about when a binomial distribution converges to a normal distribution. Sorry. When a binomial is converges to a Poisson. Okay, this have already been discussed in the fourth week lecture. Okay, so these are some of the approximations used. Now we have some more distributions, not some more actually. We have log normal distributions actually. It is actually derived from the normal distribution, and the definition for this is like suppose we may say like if x is a random variable, this follow log normal distribution with parameter mu and sigma square if log of x, you may call it y even, log of x follows normal distribution with mean mu and variance sigma square. Okay, so a random variable x is said to be log normally distributed when the log of that random variable is normally distributed with the same parameter value. Okay. So this is the log normal variate and log normal distribution. Okay. Obviously, its PDF is also kind of similar in nature, like 1 upon sigma x under root 2 pi. The x is extra introduced in the denominator term, e to the power minus half, which is same as in the normal distribution. It is log of x minus mu upon sigma whole square. In normal, it is x minus mu upon sigma. In log normal, it is log x minus mu upon sigma whole square. Right? So this is the case here. X is greater than 0, sigma is greater than 0, and mu is totally real number. Okay. So this is the PDF for the log normal distribution. Also, its PDF is not in closed form. Okay. So this is the case. We have it's like mean and variance as well. The expected value for the log normal case is like e to the power mu plus sigma square by 2. The variance of this distribution is like e to the power 2 mu plus sigma square e to the power mu square times minus. Okay. So this is the mean and variance, which is obviously not in a very simpler form to remember, but this is the mean and variance for the log normal variate. Okay. Also, it's a kth order central moment, non-central moment actually. It's kth order non-central moment have also a fixed form, which is k times of mu plus half of k square sigma square. Okay. That is its moment generating function, not this one. It's mxt. Okay. This is the moment generating function for the log normal distribution. Also, we have one more note for the log normal distribution. Like in normal distribution, we have seen that all odd order central moment have 0. But here, moments for all order of log normal distribution exists. Then moments of all order for log normal distribution exist. Okay. But in normal distribution, odd order moment does not exist. Okay. And we have one more thing to discuss, that is transformation of random variable. This topic is discussed in next week, but there is one or two questions related to this topic. That is transformation of random variable. Okay, so suppose x is a random variable. X is a random variable RV, which is continuous. Obviously, for continuous case we have discussed. We will discuss in continuous case. Okay, x is a continuous random variable, and its PDF suppose is fx. Okay, and we will transform this random variable via some functional form, which is y is px. Okay, y is a transformed random variable derived from x, which is vx. So its PDF, the PDF of y is like fx of xy, x in terms of y obviously, and it's the Jacobian term, which is dx upon dy. Okay, this is the simplest form if we have two conditions. The first one is the function y equal to vx is Continuously differentiable. Continuously differentiable implies like its differentiation is continuous. And the second condition is like either non-decreasing or non-increasing. Or non-increasing. Okay. If these two condition holds by this transformed equation y equal to vx, then we can directly use this expression gy equal to fx y and multiplied by its Jacobian dy by dx by dy, sorry. Then we can directly calculate the PDF for the transformed random variable. Okay, when these two conditions hold. So these are some of the topics that have already discussed in week 5. Now we will solve some numericals. If anyone have any doubt up to this point, please ask. Otherwise, we will solve some numericals based on those topic, and then you may ask there as well. Anyone? Okay, then we have some numericals. The first one is like a linkage component x follows normal distribution with mean 12 and it's 0.01. So that means it is nothing but variance. Okay, 0.01. Now let y, which is transformed from the random variable x as y equals 20x plus 3. Now we need to find or calculate the probability that 239 to 241. That means we have a linkage component x which follows normal distribution with mean 12 and variance 0.01. Now we have a transformed random variable y which is equal to 20x plus 3. We need to find the probability that y lies within 239 to 241. Okay, a simple question. So let's solve. Now, as we have already discussed, like you people may remind that if x follows normal mu and sigma square, then y, which is equal to ax plus b, follows normal with a mu plus b and a square sigma square. So using this property, that is the linearity property of normal distribution, we may find y here as normally distributed with 12 into 20. So 12 into 20 plus 3, it's the mu. And sigma square is like 20 square into 0.0. Okay, so that means y follows normal distribution. It's 243. Okay, 243 and sigma square is 400 into 0.1, that is 4. So that is mu y equal to 243 and sigma square y equal to 4 implies sigma y equal to 2. Okay, so these are already given. Now we need to find 239 to 241. The probability within 239, 241. Okay, so from here, always remember, since we do not know, like it is like this, na 239 to 241, it's fy y dy. But since it is not integrable, so we use normal table, obviously. So how? It's like first we standardize. Okay, so this can be written as like probability as 239 minus the mean value is 243. 243 upon the standard deviation 2. It's y minus mu y divided by sigma y, and it is 241 minus 243 divided by it's 2. No? Okay, so it is standardized now. So it comes out to be like 239 minus 243, it's minus 4 divided by this, so minus 2. This approximation is usually denoted as Z. This transformation is actually denoted as Z, and it is minus 1. Okay, 241 minus 243, it's minus 2 divided by 2 comes out to be minus 1. So since we have already discussed this, okay, in this table actually, here, Z lies between minus 2 to minus 1. Okay, so this one, minus 2 to minus 1. So it's 13.59. So without any doubt, you can directly write here like 0.1359, or you may also use normal table. Okay, you may also use normal table if you want. Okay, so it comes out to be like, since it is symmetrical in nature, so let me erase this from here only. Okay, since it is symmetrical, so you may write it's Z. Okay, so that means minus 2 to minus 1 have the equal probability distribution as 1 to 2. Okay, so this is like phi 2 minus phi 1. So from the table, okay, let me first draw a table here, sorry, a curve here. Okay, so it's 1, it's 2. Okay, so we need to find the area under this one we need to calculate, and we have a table like this. If you may see, we have table like this, 0 to up to that point, 0 to Z. Okay, so that means let me draw here as well. So maybe this kind of curve I have drawn in the below side. So it's 1, it's 2. So from the table, what we find that phi 2 comes out to be like this, and phi 1 comes out to be like this. So the phi 2 minus phi 1 is our required probability, which is 2 minus 1. Phi 2 minus phi 1, that means, okay, this is phi 2 minus phi 1. Okay, now let's see the values at phi 2 and phi 1. So from the first column, actually, you may find that it's 0.0, 0.1, 0.2. These are the values. And it's the 0.00, 0.01. So if I want to see 0.73, then that means first in the first column, 0.7 here, and then 0.03 here. So the cross section is like this. So 0.73 has the value 0.2673. Okay, so this is how we see the normal table. Now, what is the value of phi 2 and phi 1? So the phi 2 is like 2.0 and 2 is exactly, so this, so comes out to be like 0.4772. Okay, so phi 2 is 4772 and phi 1 is like 3413. Okay, so those value can be written here from the normal table. So phi 2 comes out to be like 0.4772 minus phi 1 is like 0.3413. And when you differentiate these, sorry, difference will be this, okay, which is same as from the curve or the graph. Okay, so this is the required probability. Hope you have understand how to solve this. If anyone have any doubt, please ask. Okay, then let's solve the next question. The next question is like, it is noted that 5% of pages on a corporate website contain error. Okay, if 100 pages are checked randomly, if 100 pages are checked randomly, find the probability that at least one of the checked pages has error. That at least one of the checked pages has errors. Okay, so this is the question. 5% of the pages on a corporate website contains error. If 100 pages are checked randomly, find the probability that at least one of the checked pages has error. Okay, so let's solve this again. Here, our random variable is like what? Number of checked pages has error. Okay, has errors. Okay, so if you may recall, like every distribution has a different kind of property, which here in this scenario, this random variable x is actually not normally distributed, it is binomially distributed. Okay, it's binomially distributed with n equal to already given 100 and p equal to 0.05 or 5%. Okay, so we are given n and p is there. And also at least one of the checked pages has an error. Okay, so at least one, what does it mean? Either one or more than one. So this means probability that x is greater than or equal to 1, either one or more than 1. Okay, and with the help of the complementation of the random variable or the property of complementation, we will find it is 1 minus probability that x is less than 1. And since binomial distribution is discrete, so this implies 1 minus probability that x equal to 0 only, because it's either 0 or 1 or 2. So yes, now it's quite simple. It's 1 minus probability that x is equal to 0. Okay, 1 minus the x is binomial distribution, so it's 100 NCX. So 100 CX is equal to 0. It's P, which is 0.05 to the power X, which is 0. 1 minus P, which is 0.95 to the power N minus X, which is 100 minus 0 comes out to be 0. Sorry, 100. Okay. So this is what? 1 minus 100C, 0 comes out to be 1. 0.05 to the power 0 comes out to be 1, and 0.95 to the power 100 comes out to be 0.0059 to 5 decimal place, for 4 decimal place. So yes, it comes out to be like what? 0.9941. So this is the simple probability that x is greater than or equal to. So it has a 99.4% probability that at least one of the checked pages has error. So approximately 100% chance. There is very less chance that it contains no error. Okay. So it's a simple question actually. Now the next question is like, anyone have any doubt, please ask. The next question is like, the study region in Central Phoenix in Central Phoenix, Arizona, recorded 10,500 asthma incident in children in a 21-month period. In a 21-month period. Assume that the number of asthma incident assume that the number of asthma incidents follows a Poisson distribution. Find probability that x is greater than, we need to find probability that x is greater than or equal to 550. Okay. Where x is the number of asthma incident in a month, where x is the number of asthma incident in a month. Okay. Also, since we are discussing about normal, so we have one note that use normal approximation to Poisson distribution. Use normal approximation to Poisson distribution. Okay. So that means we need to use Poisson distribution, sorry, normal approximation of the Poisson distribution. And we are given this that 10,500 asthma student in 21 months. Okay. And since in the last class, we have discussed about Poisson in the Poisson distribution is used when we are dealing with a rate kind of parameter, a rate kind of incident. Okay. So yes, and also we are given here, if you may see, you may find x is a random variable in a month. It is a kind of rate. And we have 10,500 incident in 21 months. So that means in 1 month, how many incident is there? So yes, now you may recall. So as you discussed, X is our asthma incident. In a month. Okay. This is the important point. In a month, we have a rate. Okay. So X is given as a Poisson distribution. with the parameter value of what? The parameter's total value is like 10,500 and the total month is 21, which is it's 500 actually. P with 500. So we have 500 as lambda value. So that means what? The lambda value comes out to be 500. Now we need to, since 500 is quite large number, okay? And in normal approximation to Poisson distribution, if lambda is large, then we may use the standardization process, okay? So now what we need to calculate the probability that x is greater than 550. So which is what? Probability that x minus mu. What is mu? It's lambda. It's under root of lambda is greater than or equal to 550 minus lambda comes out to be 500. Under root of lambda is under root of 500. This is what we can write. Now let's write it as z because the standardization random variable is usually denoted as z is greater than or equal to its 50 divided by under root of 500. Okay, which comes out to be 22.36 up to 2 decimal place. Okay. Now there is one actually like conceptual thing that we need to focus, but let me first write or solve this in this manner and then I will add those points as well in the same solution. So here is like it's very simple actually. Z is greater than or equal to 50 upon 22.36, which comes out to be 2.24. Okay. It's greater than actually. Okay. So always try to draw the normal curve when you are solving these kind of questions. So you have an image of the question. So this is the kind. Okay. And I am talking about Z. So this is the Z value. This is Z equal to 1. This is Z equal to 2. This is Z equal to 3. So it's like Z equal to 2.24 is comes out to be like this here only. Okay. So this is 2.24. And what we need to find greater than this value. Okay. So we need to calculate this value. Okay. And since we have a different kind of table actually. Okay. So what that is mean? It means like if we have like probability that Z is less than or equal to Z, this kind of table in the above. So and the area from here to here or the probability that means from here to here is half 50%. Okay. So first from the table, we calculate the area for these. Okay. And then subtract from the half. Okay. So that is our required answer in this scenario. So let's do this. So this can be like written as what? It's 0. Like 5 minus probability that Z is less than 2.24. Okay. Now it's 0.5 minus it's 2.24. So again, let's go to the table, normal table, 2.24. So it's 2.2 and it's 0.04. So it comes out to be okay. So it's 2.2 and it's 0.1234. It's this one 0.4875. Okay. So 0.4875 is our value. Minus 0.4875. So yes, when you are solving, you will find the probability that x is greater than or equal to 550 comes out to be 0.0125. Okay, so this is the case. So up to this point, if anyone have any doubt, please ask. Okay. If not, let me introduce one more topic in this question only. Okay. Since we are discussing about like Poisson distribution, okay, which is discrete in nature, and then approximate it to normal distribution. So there are one continuous correction. Okay, the correction for the continuous from discrete to continuous random variable. So we usually add or subtract here. We usually write it like this: z is greater than or equal to, it's like 50.5 divided by 22.36, or greater equal to, it's 49. It's 49.5 divided by 22.36. Usually, when we are discussing about discrete to continuous, the correction for the continuous random variable is like this. And when you do like this case, okay, then in that scenario, the probability comes out to be kind of equal actually 0.01196, which is up to 3 decimal point 0.012. Okay, so that means kind of similar. Okay, so this is how we use the approximation. So any question up to this point? No? Okay, then we will solve the next question then. The next question is like the time until recharge for a battery. The time until recharge for a battery in a laptop computer under common conditions is normally distributed with a mean of 260 minutes and a standard deviation of 50 minutes. Okay. Then what is the third quartile of battery life? We need to find what is the third quartile of the battery life. Okay, so that is we need to calculate Q3. So we are given X random variable, which is time to recharge the battery. Okay, and we are given it follows the normal distribution with average value of 260 minute, and the standard deviation is 50. So we need to write 50 square, because always remember the standard notation, and normal mu sigma square, 260 and 50 square, not 50. Okay, so this is given to us. Now we need to find the third quartile. What is the third quartile of the battery life? So obviously we need to find probability that X is less than or equal to Q3. And this is what already it is mentioned that third quartile. which comes out to be 0.75. Okay. So yes, this third quartile can be written as like this. It's minus infinity to like 0 plus zero to Q3. Okay, equal to 0.75. Because I have written this, the last line, because we have a different kind of table. Okay, on internet you may find a different table which contain from the minus infinity to x point, the probability under minus infinity to x, like this. The you may find the table in which like this probability is given. Okay, and we have the table which have only this probability. Okay, so this probability that x is less than or equal to q3 can be written in the next form. Okay, so also you may remember this comes out to be 0.5 because of the symmetricity property of normal distribution. So yes, we can write it like this: 0.5 plus probability that 0 to h to q3 equal to 0.75, and then probability that 0 to x to q3 comes out to be 0.25. Okay. Now, since we do not have the q3 value, but we have the probability value at q3, okay, which is 0.25. So now let's go to the question. Okay, and also we can write like this, na? Probability that q3. Okay, I have done one thing. I have missed one thing actually. This is a normal variate. Na? Let me first convert in a standard normal form. I have forgotten actually. So that is like x 0 minus that can be 0. So x minus its mu upon sigma. Okay, that is, let me write it directly: z less than q3. So it's q3 minus mu. What is mu here? 260 and 50. It's 260 upon standard deviation is 50 is equal to 0.25. So let's see the table again where the probability value is either 0.25 or it's near to the 0.25. So let's see. Okay, so sorry, I think the table has misaligned. No, it's okay. Let me erase this first. Okay, so we need to check what the value whose probability is 0.25, so or nearly 0.25. So let's see. It's 0.25 is like either this or this. Okay, any value we can consider. So this is what? This is 0.6 and 0.07 or 0.08, whichever you can want, you can take. Okay, so the value for that is like since probability that z is less than 0.68, for example, comes out to be 0.25, I think 2.13 or 17 is there. Okay, so this is the case. Since the right hand side is equal in star and double star, so from there, that means what? So that means it's Q3 minus 260 upon 50 comes out to be 0.68. Now it's Q3 equals 0.68 multiplied by 15 plus 260 It comes out to be 34 plus 260, and then Q3 can be calculated as 294. So the third quartile value comes out to be 294. This is our required answer. So is it okay up to this point? Anyone? Anyone have any doubt? The same question can be asked for the median as well, 2 2. And then you may find that it comes out to be 260 only. Okay, you may solve this by yourself if you want. You may find out it comes out to be like what? Here it's 50%, probability that x is less than or equal to 50%. So that means what? Sorry. It is directly comes out to be 260 because you may remember or you may know that for the normal distribution, mean is equal to median is equal to mod, because the normal distribution is symmetrical in nature. Okay, so you may find this value as well because mean is 260. So that means median is also 260 and mod is also 260. Okay. If no questions, let me solve some other question. Now there is one more question, a similar kind of question. Okay, the previous one kind of, but have a simple changes. The question is the IQ level of a group of students. The IQ level of group of students is assumed to be normally distributed with the mean 110 and standard deviation always remember, most of the time in question it is used standard deviation, but during the expression we use either standard deviation or variance, depends on where we will use those information. Okay, 110 with standard deviation is like 50. Okay, now the probability that a randomly selected student, the probability that a randomly selected student has an IQ of at least it's 110 plus k. Okay, the randomly selected student has IQ at least 100 plus, sorry, 110 plus k. That is the mean value plus k. Okay, is the probability is given as like 0.2033. Find the value of k. Fine. Simple question. Okay, just you need to maybe kind of use some, what we can say, mental exercise you may find. Okay, so the first thing is we are given the random variable x, which is IQ of students. Okay, and this is normally distributed with the mean 110, and the variance is 15 square. That comes out to be 225. You may write if you want. Okay, So this is the information we are given. Also, we are given the probability is this. The probability, at least this. The probability that x is greater than at least, that means greater than or equal to 1110 plus k. Okay. Since we are dealing with normal distribution, we can either escape or can take greater than or equal to or at least. So that means okay, x is greater than this. This comes out to be 0.2033. Okay. Now we have a table like this, na? Like 0 to up to the point z. So we can write it like this. If you want, you can write the probability that x is less than 110 plus k. Okay. Or okay, let me wait. Me write first standardize the value so that it's simpler for us. Probability that x minus 110 divided by 15 is greater than or equal to 110 plus k minus 110 divided by 15. It's 0.2033. Okay. So we can write what z is greater than or equal to 110 can be cancelled out. It's k upon 15. Okay. Z is greater than or equal to k upon 15 comes out to be 0.2033. Okay. Now use the complementation property. So probability that z is less than k by 15. Okay. You can use equal to if you want. This comes out to be what? Not it's this. It's now 1 minus 0.2033. Up to this point, is it okay? Okay. Just using the complementation property. So obviously it can be solved and find out to be 0.7967. So probability that z is less than or equal to, you may write k upon 15 comes out to be this. Okay. The same concept now. What we have used in the previous question. This z k by 15, z is less than k by 15. So that means minus infinity to as well. So that means we can write minus infinity to z to 0 plus because let me write first plus 0 to z to k upon 15 is equal to 0.7967. I have used this particular thing because of we have a table that has only positive s part. Okay, that has 0 to the form table. Okay, so you can write like this. Now again, this comes out to be 0.5 plus probability that 0 is less than z is k by 15 comes out to be 0.7967. Now the probability that 0 to z to k by 15 comes out to be like 0.2967. The simpler form, the phi of k by 15 is 0.2967. Okay. So the next step is to check the nearest possible value having the probability 2967. Okay. So let's go there on the table. You may use different table if you want. Okay. So 2967. So the probability, the nearest probability is 2967. You may find out exact same value. It's 2967, which is 0.8 here and here 0.03. So it's 0.83 comes out to be 0.83. Okay. So that means what? Pi 0.83 has the probability 2967. Again, 1 and 2 can be like having the similar right hand side value. So k upon 15 have 0.83 value, and from there only we can calculate 0.83 multiplied by 15 comes out to be 12.45. Okay, so the value comes out to be 12. Okay, so up to this point, anyone have any doubt? Please ask. No, then let's solve the next question. The next question is like the diameter of a dot produced by a printer. Diameter of a dot produced by a printer is normally distributed with a mean diameter of the mean diameter of 0.005 centimeter and with standard deviation of 0.001 centimeter. Okay, the dot produced by the printer as the normally distributed with mean diameter is 0.005 centimeter and the standard deviation is 0.001 centimeter. We need to find what is the probability that a diameter is between diameter is between 0.0035 and 0.0065 centimeter. Obviously, okay, that's very simple question actually. So let's solve this quickly. We are given like the dot size, no? Like the random variable, the dot size produced by the printer. Okay. Also, we are given it's normally distributed with mean 0.005 centimeter with the variance 0.001 whole square because its standard deviation is 0.001. This is the given. We need to find the probability that it lies within 0.0035 to 0.0065. Just very lot, like decimal numbers are there. So let's do this. Let's standardize 0.0035 minus 0.005, the mean value, divided by 0.001, the standard deviation value. It's x minus mu upon sigma comes out to be z. It's 0.0065 minus 0.005 divided by 0.001. Okay, this comes out to be like what? It's 0.0015. 0.0015 divided by 0.001. It's that it's zero, it's minus actually, and this one is plus one. 0.0015 whereas 0.001. And yes, after solving, you may find it's minus 1.5. Z, it's 1.5. Okay, this is nothing, just simple calculation only. Okay, we have standardized the random variable x to z with the values like minus 1.5 to 1.5. Okay, now since we know that the normal distribution is symmetrical in nature, so that means what? That means probability that minus 1.5 to z to 0 plus probability that 0 to z to 1.5. This can be written like this. And because it is symmetrical in nature, the probability value of this and this comes out to be equal. That is the property of the normal distribution. Okay. So use this. We can write like this, or 2 times of probability of 0 to z to 1.5, because we have the table having the positive value only. Positive value is there only in the table. So we can write like this, twice of this probability, which is twice of pi of 1.5. So let's see the value at 1.5. It's 1.5. It's 4332. It's 4332. It's twice of 0.4332, which is the probability that 0.0035 x 0.0065 comes out to be like what? 0.8664. This is our required probability. That means 86.64% of the dot has size 0.0035 to 0.0065 centimeter, obviously. Okay, so this is the answer. So any doubt up to this point? Any question? No. So let's solve one more question on the same topic, some different approach. This question is like, in a normal distribution, in a normal distribution, 31% of the items are under 45. Under 45, and 8% of them are over 64. Okay, so that means 45%, sorry, 31% of the items are less than 45 and 8% have more than 64. Also, we need to calculate the mean and standard deviation of the distribution. Find mean and standard deviation of the distribution. We are given some values actually already given in the question, because we can use those value directly. Like the probability that z is less than 1.4, it's minus 1.4, comes out to be 0.08. Okay, and the probability that z is greater than 0.5, that can also be seen from the table if you want. I have directly written here because most of the time I need to go up. Z is greater than 0.05 comes out to be 0.31. Okay, these both are given in the question actually. Okay, so we need to find the mean and variance. It's kind of simple question again, because we have two conditions. We need to find two values. So yes, two equation, two parameter values unknown. So let's solve this. So we are given x follows normal distribution with mean mu and variance sigma square. Okay. We are also given the probability that x, we are given less than item under 45. So x less than 45, it has the probability 0.31. Okay. And x is greater than 64, have probability 0.08. These two are given to us. Okay. So let's take one by one. The first one is like probability that x minus mu upon sigma. X minus mu upon sigma is less than 45 minus mu upon sigma. it comes out to be 0.31. Okay, so that means probability that Z is less than 45 minus mu upon sigma comes out to be 0.31. 31, not 35. 31. Okay, so this is our first equation, I mean to say. Now the second one, again, we can write the Z is greater than 64 minus mu upon sigma equals 0.08. Okay, question number two. Equation number two, I mean to say. Okay, so we have these two quantities. Now we are given some condition actually, less than 1.14, 0.08. Okay, and here Z is, where we can write like this. If you want, you can write like this. Probability that Z is greater than 1.4, it also has 0.08. If you remember, you may find that probability that Z is greater than 1.4 has the probability 0.08. Okay. And because of the symmetricity, the property of symmetricity, and the proper probability that Z is less than 0.5 comes out to be like 0.31. Again, is it okay up to this point? Okay, so from these equation, the Z is greater than 1.4 comes out to be 0.08, and here Z is greater than 64 minus mu upon sigma has equal probability 0.08. So from those two equations, we can write directly, like comparing those, comparing with given conditions. Okay, so that means 64 minus mu upon sigma comes out to be 1.4, and similarly 45 minus mu upon sigma 0.5, and 45 minus mu upon sigma 0.5. We have two equation in two variable. Now we can easily solve this question. It comes out to be like 64 minus mu upon 1.4 and 45 minus mu equal to 0.5 sigma. Okay, so let's write in this manner. So it's 64. Okay, it's like mu plus 0.5 sigma comes out to be 45, and mu plus 1.4 sigma comes out to be 64. Let's equation A, equation B. So subtract equation A from equation B, we will get what? From B minus A, we will get 0.9 sigma comes out to be 64 minus 45 comes out to be 19. 19. Okay. I think there is one thing is missing, maybe or not, I'm not sure. Okay. There is one thing is missing actually here, because here this is Z is greater than 0.05. It comes out to be, this one is minus, no? So from here it comes out to be minus. So yes, it's minus. So it's overall actually plus. So it's 1.9 sigma. So from here only, sigma can be 10. Put the value of sigma in any of the equation, you may find mu equals 50. It's simple calculation, so I risk it. So is it okay up to this point? Okay. I have one more question actually. Okay, let me see where is the question. I think I have completed all the question perhaps. Let me see, I have one more question. That is quite good question actually. Yes, this is the question. Okay, this is the last question. Uh, we are given like we have a random variable x. So let x be a random variable with PDF with probability density function is like 1 upon pi 1 upon 1 plus x square for x and take all real values. Okay. Find the PDF of x square. X square. Okay. So this is a question of transformation actually. Direct, we need to find the PDF of x square. Okay. So let's solve this question. We are given the PDF is like this 1 upon pi 1 upon 1 plus x square. Actually, this is a PDF of standard Cauchy distribution. Which is C10. This is the PDF of standard Cauchy distribution having the parameter value 1 and 0. Okay, so we need to find the PDF of a transformed random variable y, which is x square. So we can directly use the CDF approach, cumulative distribution function approach. It's like what? Suppose this is the CDF, and you know the probability. The formula for CDF is probability that y is less than or equal to y. This is the formula for the CDF. Okay. So from here we can write like what? Y equal to x square is there. Na? So x square is less than or equal to y because capital term is for random variable and small term is for a random sample, which is ultimately a number. Okay, which is ultimately a number. So x square is equal to small y, which is kind of a value 0.2, 0.579, something. So from here only we can write like this probability that it's minus y, it's x is x, not x square, it's y. Okay, we can write like this. That's simple mathematics up to this point. And obviously, this can be like what? Y, y, it's fx dx. Simple question. Same thing, just formula. Now we have a question actually, or we can write like this. Let me write it's 1 upon, it's not 2 pi, it's pi 1 upon pi 1 upon 1 plus x square dx. Now see the function 1 upon 1 plus x square. It's an even function actually. Okay. Since like f of x equals f of minus x, that is even function. And since if it is an even function, we may write like this. It's 0 to under root y. Okay. Twice. Because 0 to my sorry, like 0 to under root y and minus root y to 0 have the same probability distribution for this case only when the function is even. So we can write like this. And now it's pi, it's 1 upon 1 plus x square dx. Simple. And if you know, you may find out it's nothing but tan square. 1 up 2 upon pi is there. 1 upon 1 plus x square has integration value of tan inverse x 0 to y. Now it comes out to be like what? Comes out to be it's 2 upon pi, and it's tan inverse root y minus tan inverse 0. So overall, the CDF, this is the CDF. Always remember, we are using the CDF approach. This is the cumulative distribution function of the random variable y. So it's tan inverse y. I mean root y. So this is our the CDF of transformed variable y, which is equal to x square. Okay. We need to find the PDF actually. We need to find the PDF. So PDF can be evaluated by differentiating the CDF simply. So the PDF of this is nothing but the differentiation of the PDF. You may differentiate actually. Okay. So it's d dy of it's 2 upon pi. And what is tan inverse of? Again, the same thing is repeated. The integration of this is 1 upon 1 plus x square. So it comes out to be like it's 2 upon pi is there. Okay. So it comes out to be 1 upon 1 plus x square. Here x is root y. So root y square comes out to be y. And then dy of root y as well because of the chain reaction. Sorry, not chain reaction, chain rule. Okay. So it's comes out to be 2 upon pi into 1 upon 1 plus y into it's 1 upon 2 root y. Okay. The differentiation of root y is 1 upon 2 root y. Simple. Just simplify this. You may find 2 can be cancelled out. It's 1 upon pi. It's y to the power minus 1 by 2. Na? And y plus, sorry, 1 plus y is there. Okay. This can be rearranged in different format as well. Okay. This can be rearranged like this because it is not in known form. Actually, it is known form, but you may not properly recognize the form. So is like it is like 1 by 2 minus 1. Okay, y to the power 1 by 2 minus 1, and the denominator term is pi is there. 1 upon pi is there, and this 1 plus y can be written as like what? 1 by 2 plus 1 by 2. Okay, this can be written like this. So this is a particular form which is beta distribution with parameter 1 by 2 and 1 by 2. This is a beta distribution of second kind, not the first kind. This is the beta distribution of the second kind. Okay. And how the PDF is like this. Let me write the PDF of the beta distribution of the second kind. See, the distribution, suppose X follows beta second kind of Mn with the Mn parameter, then its PDF will be like 1 upon beta Mn and x to the power m minus 1 and 1 plus x to the power m plus n. Okay. So here m equal to 1 by 2 and n equal to 1 by 2. So m plus n comes out to be 1. Okay. Also beta 1 by 2 and 1 by 2. The beta function has value gamma half upon gamma half plus comes out to be gamma half value comes out to be pi actually. Sorry, root pi, I mean to say. And root pi and gamma 1 comes out to be 1. So it's beta half comes out to be pi. So this is pi here, 1 upon pi, and y to the power m minus 1 and 1 plus y to the power m plus 1. So it overall comes out to be a beta distribution of second kind. with parameter 1 by 2, 1 by 2. So is it okay up to this point, or is there any question? See, this is the question. We start with a Cauchy distribution, okay? And then we define a transformed random variable by y equal to x square. Then the PDF of the transformed random variable comes out to be beta distribution of second kind, okay? So that means one distribution is approximated to another distribution via transformation method, okay? Is it okay up to this point? So anyone have any doubt up to this point? Please ask now, because these are the questions I have prepared to solve here. If you people have any doubt or anything want to ask or share, you are welcome. If not, then we can conclude our session here only. Anyone? Okay, so let me stop the recording first.